Hello everyone, and welcome to the part 2 video lecture of the week 6 module. In this video we're going to go over, we're going to begin where we left off with discussing how to weight variables in a given data set. Then we're going to discuss cluster samples, non-probability samples, what we can and can't learn from sample data, and then we'll end with a brief discussion on kind of some statistics that we're going to be learning moving forward, such as sample errors and standard deviations. So, picking up where we left off, we are over sampling engineering majors, so we have enough observations to make statistical inferences, but also imagine that one attribute we really care about from engineering majors is generally super high. Okay, so just keep that in mind as we go through the next slide. So to overcome sampling bias that would inflate GPA, we have to weight the average GPA by group. And the way that we do this is that we multiply the mean or the average GPA for each of the majors by the proportion of the population of each major. So let's take a look at the equation to see if this kind of helps you understand what we're talking about here. We take the strata population, right? So let's say we wanted to start with liberal arts majors. So that would be 500 because that is the population of that specific strata, that specific group. We would divide that by the total population, which we know is 800 based upon this data here. And then we would multiply that proportion that we've just created by the attribute of interest. And this would create a weighted attribute or a weighted variable. So let's look at GPA, okay? The first thing that we have to do, if we want to weight GPA by major, first, we have to determine the strata proportion. So what proportion does each major constitute of the total population? And here we're just doing some really simple division. So there are 500 liberal arts majors out of a total of 800. That's 62%. There are a total of 100 engineering majors. We divide that by 800. Again, so we're just doing simple percentages here. Engineering majors constitute 12% of the total population. And then business majors, there's 200 of them. Divide that by 800. 25% of all of the majors are business majors. So here we have our proportions here. You could add those all up. They would equal 100. And what we're going to do is we're going to take these proportions and we're going to multiply that with the average GPA of each of the groups. Okay, so we can see that the average GPA among all liberal arts majors is 2.5. We can see that the average GPA of all engineering majors is 3.3. See how much higher that is than all of the other ones? And then the average GPA of all of our business majors is 2.7. So the final step here, we take that proportion that we created and we multiply that times the average GPA. So this should all be some pretty simple math, right? We're just, we're weighting these values, these attributes, these variables in a way that is representative of how much they constitute the entire population. So we know, let's look here, we know that liberal arts majors constitute 62% of the entire population. So we're going to multiply their average GPA, which is 2.5, times that proportion. We're going to do the same thing with the engineering majors. We know that engineering majors constitute 12%, 0.125. We're going to multiply that times their average GPA, 3.3. And then we're going to do the same thing with the business majors. We know that business majors constitute 25% of the total population, and we're going to multiply their average GPA, 2.7. Once we have done the order of operations here, what this means is that we take our liberal arts majors, and once we have weighted their GPA based upon their proportion of the entire population, that their average GPA is about 1.56. Engineering majors We're going to bring that way down. That's 0.412. And then our business majors to 0.675. And we add those all up together. And what this sampling statistic here is telling us is that the average GPA from the entire college is probably about 2.65. And this is taking very careful consideration into the types of students that we're dealing with in our sample. Since engineering majors tend to have really high GPAs, but there's not a whole lot of them, we need to recalculate these values in a way that's representative of the population that we're trying to study. And even though we haven't really done a deep dive into descriptive statistics yet with the mean, the average, the median, or the mode, one thing that is worth keeping in mind is that when we're talking about averages or the mean, averages are significantly influenced by outliers. So if you have one value that's really, really high and you're trying to calculate the average, just having that one outlier in your data is really going to drive up the mean because all elements of that equation are treated equally. So just to, kind of illustrate this point, if we just took these GPA statistics, so on average for each of these college majors, if we just took these figures, 2.5, 3.3, and 2.7, and we just added those up together and divided them by 3 to try and get an estimate of the total GPA of the college, then that would equal 2.83. So that's pretty high, 2.83. But that's a pretty high GPA, and we can see, based upon the weighted value that we calculated, that's a much more accurate representation that is, we have removed the influence of outliers, or we've removed the influence of one specific group with not a whole lot of cases in it having really high values. So I hope that this is a good example. I hope you understand the purpose of weighting values, why we would do something like this. Again, there will be lots of examples in the homework journal on how to weight attributes or variables by specific groups or strata. But again, it's just really simple math, calculating proportions and then multiplying those by values of interest. So I hope that that's nice and clear for everybody. Again, if you have any questions, please be sure to post those in the discussion board. Okay, I've got just a few more to get through, and we're almost done. The next type of probability sample that I want to discuss is a cluster sample. These are generally less common in the social sciences, but nonetheless something you could absolutely run into with future research projects. But a cluster sample is a probability sample in which the sampling frame initially consists of clusters of elements. And since only some of the elements are to be selected in a sample, researchers are unable to list all of the elements at the beginning of the research process. So essentially what this means is that the randomization of the sample is kind of conditional upon the characteristics of the cluster. And you might be thinking to yourself, oh my God, what are we talking about? What does this even mean? So one really common example is, of using cluster samples is when people are doing field research, and particularly in metropolitan areas or things like that, where they want to interview people, maybe metropolitan residents in a large residential area. So let's imagine that a researcher wants to take an opinion poll of 100 residents living in a city, but has no list for residents in that city. So they start with a map and they identify all of the residential blocks in that city. So that's kind of represented in this graph here. Each block here technically represents what we would call a sampling unit. So this block 1, right, that represents a block with X amount of houses on it, block 2, block 3, block 4. and so on and so forth. So we have enough resources to interview 100 residents, and all of our potential elements, the people we are potentially going to interview, are all kind of randomized throughout this city block with 25 blocks on it. So what can we do to make sure that, first of all, we've randomized the selection of blocks that we choose in our city? Those clusters, that we randomize those clusters, and then we randomize the dwelling units within those blocks. So this can be kind of complicated. Again, this certainly isn't going to apply to anyone's research paper in this course, but it's nonetheless a good method to at least be aware of. So for no particular reason, let's say that we know that we have enough resources to at least, interview people at 12 different blocks. Okay, so we know that there's a total of 25 blocks. That's our population. And we have enough resources to confidently sample 12 of those blocks. So our desired sample size for the cluster is 12. And say we use some randomization. Let's say we use simple randomization, right? So we just put the numbers 1 through 25 in a computer program, and we said, I want you to randomly spit out 12 of these numbers back to me. And it comes back with 1, 2, 5, 8, 10, 11, 12, 16, 19, 20, 22, and 23. I didn't need to read all of those out, but I felt compelled to do so. All right, so now we've got our 12 blocks that we think are a really good random representation of the city in general. And now, remember, we can only interview 100 participants. So how are we going to make sure that we get just 100 participants and that we're equally sampling those from all these different blocks? And so here's some data that just shows you these are the number of dwelling units per block. So I need to take a random amount from each of these dwelling units until I get to my perfect desired sample size of 100. And there's a variety of ways that we could do this. We could do the systematic random sample. So I think if we add, is this correct? Yeah. So if we added all of these dwelling units together, that would mean we have a total of 600 houses in our 12 blocks that we've just randomized, but I can only interview 100. So without belaboring the point, we would take all of our dwelling units, and we have this data in a spreadsheet, and we would just tell the, software program to keep 100 of these observations among all of these different dwelling units and to keep that balanced. But ultimately, we would end up with this. We would end up with like a perfectly, distributed random number for each dwelling unit from each block. So block 1 has a total of 23 dwelling units, but ultimately what made it into our sample? 8 cases. Block 2 has a total of 35 dwelling units, but we took a perfect proportionate sample of that from the 35. 9 made it into our final sample over and over and over again. And if you added up everything from this column, it would equal 100, which is our desired sample size. And there's all kinds of things that you can do, to make sure that this is the best method that you could possibly do for sampling of your population of interest. So we could compare our random sampled blocks to the true in of the dwelling units from our 12 blocks, our 12 clusters, and we can see, right off the bat, I can see that orange, which I guess is block 10, from our perfectly random distribution has undersampled block 10. Another one, this teal one, I think that's block 5, that looks way smaller in our random sample than the actual sample. So this would actually probably be a really good place to use a a proportionate stratified sample if there were characteristics of each of these blocks that we thought were theoretically important or might influence people's attitudes about whatever it is that we're asking. But this is just kind of an example of cluster samples and some of the issues you might run into if you're trying to, sample clusters, and making sure that you have a representative sample that accurately reflects the population you're trying to study. And just because I could not resist, apparently, making another table, I could show you exactly what that would look like. So, we know that we have the total dwelling units, which is 600. Our desired N or sample size is 100. So if we calculate that sampling fraction, we end up with 100 divided by 600, which is 1/6. So that is our proportion that we're going to multiply everything by. And so we could apply that here, right? So we've got 23 dwelling units in block 1, multiply that times 1/6, and we end up with 4. And we do that with block 2, and we get a proportional sample of 6 from block 2, and so on and so on and so forth. So you could actually compare that, again, because I could not resist making the graph as well. You can compare that to the proportional sample here, which looks a lot more representative of the dwelling units from our selected blocks and clusters. So, again, depending on the characteristics of the blocks and the research question that you were asking, you would have to make the determination as the researcher as to whether or not the proportional sample with an N of 200 was more appropriate, or if it was the randomly sampled households where each block has about 8 or 9 cases each, whether or not that's the best sample for the population data, and ultimately choose the one that has the least amount of bias in the estimates. Okay, and the last thing that I want to talk about today are non-probability samples. So just as we discussed from probability samples, where there is a known probability of being selected in the sample, non-probability samples are distinct and unique because it means that each element in the total population has an unknown probability of being selected. And sometimes these methodologies and approaches are unavoidable, and it's the only approach available to the researcher. But as a general rule of thumb, non-probability samples tend to have more bias than probability samples for reasons that we will discuss in just a moment. There's 2 types of non-probability samples that I'd like you to be aware of. First is a judgment sample. So here the researcher is simply making a judgment of who they are going to include in their sample. So generally, you see some research done where people will interview a small number of congressmen. Maybe it's the most senior congressman that someone is interviewing to ask them about their tenure in office and what it's like to be an incumbent for such a long time. Obviously, not every congressman has an equal chance or probability of being included in that sample because the researcher has very distinct, narrow objectives or justifications for, why certain congressmen are included in the sample and why others might not be. Another example would be, interviewing prominent journalists or, any prominent individual in some field that you were interested in learning more about. Not every journalist would have an equal probability of being included in your sample because you're specifically examining prominent journalists for one reason or another. Another example is quota samples. These are actually pretty common in some fields, and they're kind of inherently problematic for a few reasons. But what's unique about a quota sample is that elements are sampled in proportion to their representation in the population. So it's very similar to a stratified proportionate sample, but the key difference is generally participants are not chosen randomly. So what does this mean? Well, let's imagine that we needed participants for a study to talk about gender-based discrimination in the workplace. And we only had enough resources to interview 100 people, but we wanted to make it, we wanted our sample to accurately reflect the true gender, population in the United States, for example. So we want equal number of men and women. We want 50 women and we want 50 men to participate in our study. So let's say we set up shop at some recreation center in the middle of downtown, and we say, okay, we're going to be selecting participants from noon to 5. I have no idea, right? So come to the rec center, stand in line, and we'll let you know if you can participate in our survey or not. I mean, this happens pretty frequently in some cases. So we got a big line of people going out the door. And as soon as, the 50th woman or the 50th man enters the door, and we have met our quota, then we are no longer going to be sampling any individuals from that specific strata or group. So again, we could think of a whole lot of reasons why some people might get there really early, right? Maybe we're thinking about single women or younger women, they don't have children. Maybe it was super easy for them to just drop everything that they were doing, come to the call, get in line early, and be a part of the study. Whereas married women, older women, women with children might have had a really hard time getting everything situated before they could come stand in line and potentially participate in this survey. So, I mean, that's just one example of how, and the same could certainly apply to the male respondents, of course, too, right? But that is just one example of how, even though this type of sample metric is under the guise of being stratified and representative of specific groups, it's conducted in a way that's inherently problematic and has a lot of potential for bias in a way that not every individual of that group has an equal chance of being included in the study or in the sample. And just to explain why the Dewey defeats Truman is on this slide, I feel like I have to mention that. A straw poll is another example of a non-probability sample. And the classic example of Literary Digest putting mailers in its magazine trying to predict whether Dewey or Truman was going to win the election. That's like a horribly flawed polling method. We kind of talked about it in this lecture already too, right? I mean, people who are hyper politically engaged, are going to be the ones who are most likely to take the time to fill out a card, put it in an envelope, put it in the mailbox, right? So that's just a really famous example of like one of the worst polling gaffes in American history, where the election results were so wrong. They were so off because the sampling frame was just awful and terrible and biased and not really random or representative. So that's why Truman is on this slide. So overall, what can samples and what can't samples tell us? The main thing that I want you to walk away from today's lecture with is understanding that we take random samples from populations in order to make statistical inferences about the population parameters that are unknown. Again, we can't interview all 300 million Americans to get a sense of Joe Biden's true approval rating. Like, it's unknowable because there's no way to interview every single American to get a true 100% unbiased estimate or a figure, an actual number of what that is. So we have to make estimates, and all of statistics, everything that you're doing in this class, in your research papers, it's all estimates, based upon the scientific method and learning ways to avoid bias or to minimize bias in a way that we can be confident in the estimates or the inferences that we're making about the true population. And so if 4 out of 10 people in our sample support Joe Biden, we might infer that the population parameter of presidential support for Joe Biden is somewhere around 40%. And this is something that we're going to talk about in a little bit more detail in the coming weeks, particularly when we get to empirical observations and descriptive statistics. But, kind of the underlying theoretical premises of some of the statistical analyses that we'll be making in this class is, based upon the idea that if we were to conduct random sample after random sample after random sample infinitely, gauging presidential support, for example, and say one sample we found that 40% supported Joe Biden. Let's say in another sample with 10 people that figure was 50%. Let's say in another sample it was 30%. And the idea is that with more and more and more samples that we conduct and more people that we include in our samples, that we will get closer and closer and closer to understanding the true population parameters. And so just to think of it this way, if we were to average our samples here, their average support for Joe Biden from each sample, so one sample it was 40, the other it was 50, the other it was 30. If we added those up and divided them by the number of samples that we had conducted, we would estimate that, okay, the average of all of these samples was 40. The true population value must be somewhere around 40. And essentially what we're saying here is that if we conducted infinite samples, we would gain more and more and more confidence in our findings and have a better understanding of what that true population parameter must be. And to say that in another way, as your book points out, it is expressed here with E representing the expected average value of P, the sample proportions, that would be equal to the population proportion. So this is kind of just a theoretical equation that tells us with repeated sampling, we expect that the average value of repeated samples to eventually equal that population proportion if we were to conduct those samples infinitely. And again, we will get into the math behind this in the coming weeks, but as our sample size increases, from 10 to 50 to 500, we gain more confidence in those results. You're probably very familiar with margins of error or standard error or sampling error when looking at a public opinion poll. And notice how the error gets smaller as the sample size increases. So when we, obviously, if we just interviewed 10 people and we said, do you support the job President Joe Biden is doing? It would be really difficult to say like, oh, I interviewed 10 of my friends and 80% of them hate Joe Biden. So that means 80% of Americans must also hate Joe Biden. Obviously, just right off the bat, we can think to ourselves, I don't think that that's the best math, right? Compared to a sample that has 500 people in it, we might be more likely to believe a poll with 500 people compared to 10 people. And that's because we have more confidence in our results. And that's denoted here with the standard error shrinking and shrinking and shrinking as a function of having larger sample sizes. So, this is one of the reasons why it's so important for everyone to have at least 50 to 100 observations in their research papers. Otherwise, we don't really have enough variance to make justified, valid, reliable statistical inferences. And one reason that this is that, again, we'll do these equations a little later. I know that this probably looks super scary, but the error, the way that we determine the sampling error is a function of the standard deviation, which tells us how much all of our observations vary from each other. So the way that we calculate the standard error is determined by this symbol here, sigma, which represents the standard deviation. So the sampling sampling error is the standard deviation divided by the square root of n. And you might be thinking to yourself, I don't understand, what's sigma? So here is here's the equation for sigma, or the standard deviation, if you are interested. We're going to work a lot with this equation later. I know it probably looks really scary now, but I just thought I would go ahead and show it to you guys and get it out of the way. It's something to look forward to. I promise it's not as intimidating as it might look, but you know, I always like to end the lectures with things to expect in the coming weeks, so that's my little treat for you guys. At any rate, that is it for this week's lecture. I've got an overview slide right here for you to review on your own time. This lecture content will be featured on the midterm examination, so please do not hesitate to ask if you have any questions. Do that in the discussion board, do that in class. I think on Thursday I'm going to try to have us work on the midterm study guide, so there'll be lots of questions about stuff like this on there too. That's it for this week's lecture. I hope you enjoyed, and I will see you guys on Thursday.